Hi, this is lesson 5 for unit 4 in chemistry, and in this lesson we'll be talking about the ideal gas equation plus how to get the molar mass of a gas using that ideal gas equation. For our lesson objective says students will be able to use the ideal gas equation to solve for molar mass of a molecule in the gas phase.
Let's begin our lesson of molar volume by talking about Avogadro's principle. In Avogadro's principle, it states that at equal temperatures and equal pressures, equal volumes of gases contain the same number of molecules. So let's say you have two balloons, and in one balloon you fill it with carbon dioxide gas, and the other balloon you fill it with hydrogen gas. Now, if both balloons have the same volume, same temperature, and same pressure, then they will also have the same number of gas molecules inside. That is Avogadro's principle. Now, if you were to release them, hydrogen gas is very light, so it's going to go ahead and float up. But carbon dioxide is a heavier gas, so it's going to go ahead and go to the ground. So even though one went up and the other one went down, they still have the same number of gas molecules inside, and that is Avogadro's principle. Next, let's talk about the ideal gas equation. First of all, before we can get to the equation, let's talk about what exactly is an ideal gas. An ideal gas is a theoretical gas. It's not a real gas, it's a theoretical gas that has no attraction between molecules, and the molecules themselves, we say that they have no volume. Now, that is an ideal gas. In reality, molecules do exert an attraction to each other, and they do have a size difference between molecules, but we're going to go ahead and ignore those things. The reason why we're going to go ahead and ignore those things is because when we take them into account, the calculations become very, very difficult, and it's a challenge to go ahead and solve for those. So we go ahead and we pretend that we have an ideal gas because we end up with just about the same answer numerically as a real gas, but with a lot less calculations. Now that we've discussed the ideal gas, let's talk about the ideal gas equation. The formula is PV equals nRT, where P is pressure measured in atmospheres, ATMs, V is volume measured in liters, N is moles, R is a constant, which is 0.082. We're just going to round it off to 0.08 liters times atmospheres over moles times Kelvin. And finally, T is temperature measured in Kelvin.
In example 1, we're asked the following question. What pressure is exerted by a gas in a propane container with a volume of 2 liters at 300 Kelvin and 5 moles of gas inside of the container? Alright, so this is an ideal gas equation. So here we have it, PV equals nRT. And P is the pressure in ATM, V is the volume in liters, N is the moles in moles, and T is the temperature in Kelvin. R is a constant. The constant means it's always the same number. It is 0.0821. We're just going to go ahead and round it off to 0.08. That's good enough for us. The unit is liters times the atmospheres over moles times Kelvin. So when we're solving for the pressure in this problem, I'm going to go ahead and put a question mark here for pressure. So what pressure is exerted by a gas in a container that has a volume of 2 liters at 300 Kelvin? That's our temperature. And the moles, there's 5 moles. Alright, so that is all the information is given to us, and we're asked to solve for the pressure. What is the pressure inside of that container? So we're going to go ahead and plug in the values into the ideal gas formula, but we might modify a little bit. So, for example, PV equals nRT. I'm solving for the P only, so I want to get rid of the V. So what I'm going to do is divide by V on both sides, and that's going to be my formula. Pressure is equal to nRT over V. So now that we got that, let's go ahead and plug in the numbers. N was 5 moles. The R, 0.08, is a constant, so you always use this value. The T, the temperature, is 300 Kelvin. And all of it is divided by the volume, which was given to us, it was 2 liters. Alright, that will give us our answer, and will be in ATM. Alright, so it's going to go ahead and be 5 multiplied times 0.08 multiplied times 300 divided by 2. So it's going to give us a pressure of 60 ATM. And that is our answer for example 1. Let's go ahead and move along to example 2. In this one, they ask you a similar question. Find the volume of gas which has 50 grams of hydrogen at 120 degrees Celsius and 44.1 psi. Alright, now this problem tends to be a bit more challenging The reason why it's more challenging is because all the units, well, they're in the wrong units. So for example, the 50 grams of hydrogen should really be in moles. So let's start with that one. So they give us 50 grams of hydrogen. We'll get to that one in a second. We have 120 degrees Celsius for the temperature and a pressure of 44.1 psi. Now, so what is the volume? Alright, so again, everything is in the wrong unit, making this problem a little bit more challenging. So let's go ahead and start working on changing the units. Alright, let's go ahead and start with the 44.1 psi. So I need an ATM. So this is what was given to me. And what I'm going to go ahead and do is, I want to change it from psi, which is 14.7, to ATMs, and put 1 ATM on the numerator. So it is 44.1 divided by 14.7 gives us 3 ATM. So that's the actual pressure in ATMs. The moles. We have 50 grams of hydrogen gas, and we needed it not in grams but in moles. So we're going to have to convert those. Alright, so I'm going to put, you see grams is given to me, so I'm going to put them in the denominator, and moles is what I'm looking for, goes in the numerator. So for every 1 mole, molar mass of hydrogen, if you go ahead and look for it, it is just 2. So this will give me 25 moles. So there we have it. Finally, the temperature. The temperature needs to be in Kelvin, not in Celsius. So we're going to get 120 Celsius, and to change it from Celsius to Kelvin, you add 273. So that goes ahead and gives us 393 Kelvin. That is the actual temperature. Great. So now we have it in the proper units, 3 atm, 25 moles, and 393 Kelvin. Now we can go ahead and plug it into the ideal gas equation and solve for the volume. For the volume, I want to go ahead and isolate it. So in our formula, PV equals nRT, I want to isolate the volume. So I want to divide both sides by the pressure so they can cancel out, isolating the V. So it's going to be V equals N, which is 25 moles. R, which is our constant, is always this value. Temperature, 393 Kelvin. And finally, pressure. Pressure is 3 atm. Alright, so what is the volume? Let's plug it into a calculator. 25 times 0.08 times 393 divided by 3 gives us 262 liters. Alright, that is our answer for example 2 for our ideal gas formula. Let's go ahead and move along to problem number 3. In this example, you have a float like the ones you see in the Macy Days Parade, and they tell you as the following. You have a float that has a volume of 1.8 million liters and a pressure of 1.1 atm at 27 degrees Celsius. Find the number of moles of gas inside of that float. So let's go ahead and work on that. Alright, write down the information that's given to us. We have the volume of this float, it's very large, 1.8 million liters. Alright, the pressure, high pressure, 1.01 atm. And the temperature, 27 degrees Celsius. Again, no Celsius allowed in the ideal gas formula. You got to change it to Kelvin. So we're going to go ahead and add 273 to it. And that's going to give us a value of 300 Kelvin. Alright, and the question is, what is the moles? So you saw it for the N. For ideal gas formula, what are we going to do to isolate the N? Well, I'm going to divide by the R and the T on both sides. So that way they cancel out, giving me the N all by itself. And so it's PV over RT. So let's go ahead and solve. N is P. P is 1.1 atm. V is 1.8 million liters. R is our constant, 0.08. And finally, the temperature, which is 300 Kelvin. Alright, once you plug it all into the calculator, let's see what we get. Alright, so in the numerator we got 1.1 times 1.8 million liters divided by our constant 0.08 multiplied times 300. So it gives us a grand total of 82,500 moles of gas that are inside of the float for this parade. Alright, let's go ahead and move along to example 4. The ask you is, find the temperature for a gas held in a 2,000 milliliter balloon with 32 grams of CaH4, that's methane gas, and 520 torr. Alright, so in this example, again, now you're looking for T temperature. So we're going to have to modify the formula a little bit to solve for the temperature. And also, all the units are, well, not the proper units, right? So let's write down all the information that's given to us. We have a volume of 2,000 milliliters. We have 32 grams of CH4. And we have a pressure of 1520 torr. And the question is, what is the temperature inside of the balloon? Alright, so let's go ahead and solve for this one. First of all, let's get all these units to the proper unit. Alright, so let's start with the 1520 torr. And we want them in ATM. So I'm going to put ATM on the numerator, and here the torr is given, so I want to cancel that out, so put it at the bottom. And that is 760. So that's going to go ahead and give us 2 ATM, and that's the pressure we're going to go ahead and use. 2 ATM. Next, for our volume, it's in milliliters. We don't need it in milliliters, we need it in liters. So we're going to go ahead and convert it. So we got 2,000 milliliters. For 1 liter, there's 1,000 milliliter. So that ends up with just 2 liters. Alright, now our moles, well, we got grams right now, and we need to change them from grams to moles. So we have our given 32 grams of methane, and we're going to put 1 mole on the top, and at the bottom the grams. How many grams? Well, the molar mass of methane, so that'll be 1C, 4 H's, 12 and 1, that's a molar mass of carbon and hydrogen, respectively, and we end up with a grand total of 16 grams per mole. So that's the molar mass is 16. So it's going to give us 2 moles. Alright, so now we got all of our values. What's the temperature inside? Alright, let's go ahead and solve for that. So we're solving for the temperature, so we want to isolate it. So what are we going to do to our formula? PV equals nRT. I want the temperature, so I'm going to divide by the N and the R. So that way they're gone, leaving the T all by itself. So it's really going to be T equals P, pressure, which was 2 ATM, times the volume, which was 2 liters, over N, which was 2 moles, multiplied times 0.08, which is our constant, and that's going to give us our temperature. So that's going to be 2 times 2 is 4, divided by 2 times 0.08 gives us 25 Kelvin. Alright, so that is our answer for example 4.
Up next, we're going to go ahead and discuss how to find the molar mass of a gas using the ideal gas equation. So on the slide it says the ideal gas equation, PV equals nRT, and the molar mass equation, which is M for molar mass is equal to lowercase m, which is mass, over the moles, which is N, can be combined to find the molar mass of a gas according to this equation, where M, which is the molar mass of the gas, is equal to lowercase m, which is the total mass of the sample, multiplied times R, which is a constant, 0.082, multiplied times the temperature in Kelvin, and you go ahead and you divide it by the pressure measured in ATM, multiplied times the volume measured in liters. Using that equation, you can go ahead and find the molar mass of a gas. Let's go ahead and take a look at some examples.
In example 5, we asked the following question. It says, an unknown gas has a mass of 48.32 grams at a temperature of 25 degrees Celsius and the pressure of 6 atm and the volume of 12 liters. what is the molar mass of the compound? So let's go ahead and write down all the information that we got. First of all, the 48.32 grams, that's the mass, that's the lowercase m. The uppercase m is for the molar mass, different from the mass. Alright, so we're going to write that number down, 48.32 grams at a temperature of 25 degrees Celsius and a pressure of 6 atm, and it's got 12 liters of volume there. I want to know what is the molar mass of it. Alright, all these numbers are in the proper unit except for the temperature. The temperature's got to be in Kelvin. So at 25 degrees Celsius, you got to add 273 to change it from Celsius to Kelvin. So that is 298 Kelvin. And that's the number that we will use when we plug into the formula. So we're solving for the uppercase M, which is the molar mass. Find the molar mass of this gas. So let's go ahead and do that. That's going to go ahead and be the mass, which is 48.32 grams, multiplied times the constant, which is always 0.08 atm, liters times atm over moles times Kelvin, multiplied times the temperature, which is 298 Kelvin, and you divide it by the pressure, which is 6 atm, and the volume of 12 liters. Alright, so you go ahead and you plug that into your calculator, and that's going to go ahead and give us the molar mass for this compound. So it's going to be 48.32 times 0.08 times 298 divided by 6 times 12. That gives us an answer of 16. Actually, I got 15.9999. We're going to round it up to 16 grams per mole. And that is the molar mass of this mystery gas for example number 5. Alright, let's go ahead and move on to the next part. In example 6, we ask an unknown gas has a mass of 6.23 grams at a temperature of 300 K and a pressure of 200 psi and the volume of 250 milliliters. What is the molar mass? Again, we're solving for the molar mass. To complicate this problem a little bit, you may have noticed that some of the units are not in what they need to be. For example, let's see, the pressure, they were given 200 psi, but we need it in atm. So I'm going to write that down. We have 200 psi, that's the wrong unit. The temperature is 300 Kelvin, that is a proper unit, good. The volume, 250 milliliters, wrong unit, it needs to be in liters, not milliliters. And the mass, it is 6.23 grams. Now I want to know what is the molar mass. Alright, so we got to go ahead and change the pressure and the volume to the proper units. Alright, so we have 200 psi, change that to atms. For every 1 atm, there are 14.7 psi. Alright, so we're going to go ahead and do that. 200 divided by 14.7, that gives us 13.6 atm. And for the volume, you have 250 milliliters. We're going to go ahead and convert them. For every 1 liter, there's 1,000 milliliters. So that gives us 0.25 liters. So that is the volume that we're going to plug in, 0.25 liters. Alright, now we got all the units in the proper units. Now, let's go ahead and plug them into the formula. Molar mass equals the mass, which is 6.23 grams, multiplied times the constant, liters times atmospheres, over moles times Kelvin, multiplied times the temperature, which is 300 Kelvin, and all of it divided by the pressure, which is 13.6 atm, multiplied times 0.25 liters. Alright, so that's going to go ahead and give us our answer. For example 6, you got 6.23, and now you multiply that times 0.08, multiply that times 300, divided by 13.6, multiplied times 0.25, gives us our answer of 43.99. So I'm going to just go ahead and call that 44 grams per mole. So that is our answer for example 6. Let's go ahead and move along to our next problem. Example 7, again they ask you for an unknown gas that's a mass of 6.25 at a temperature of 87 degrees Celsius and a pressure of 1.5 atm and the volume of 4 liters. What is the molar mass of this compound? Alright, so let's go ahead and solve this problem as well. Alright, so what do we know? We know that mass of this compound it is 6.25 grams. We know the temperature, 87 degrees Celsius, but that's not the proper unit, right? It's got to be in Kelvin, so I'm going to go ahead and add 273. So that gives us 360 Kelvin. The pressure is 1.5 atm, so that's correct. And 4 liters, so that's the proper unit. Alright, great. We have everything in the proper unit now. Let's go ahead and solve for the molar mass. Plug them into the formula. So molar mass equals 6.25 grams multiplied times the constant, 0.08, liters times atmosphere, over moles times Kelvin, times 360 Kelvin, over a pressure of 1.50 atm multiplied times 4 liters. Alright, there we have it. Plug all of that into your calculator. 6.25 times 0.08 times 360 divided by 1.5 times 4, close parentheses, equal 30 grams per mole. So that is the molar mass of this gas. Alright, let's go ahead and move along to example 8. In example 8, again you're solving for molar mass. They ask you an unknown gas has a molar mass of 1.81 grams at a temperature of 400 Kelvin, a pressure of 1,520 torr, and a volume of 500 milliliters. What is the molar mass of this compound? Again, the units are wrong, so it makes the problem slightly more challenging. So the mass is 1.81 grams, 400 Kelvin for the temperature. Great. Torrs, we have 1,520 torr, so we need to change those to atm. So for every 1 atm there's 760 torr, so you go ahead and multiply, divide, you get your answer of 2 atm. So that's our pressure. It was 1520 torr, but we're going to write it's really in atm is 2 atm. Alright, for the volume we have 500 milliliters, and in 1 liter there's 1,000 milliliters, so it is 0.5 liters, and that is the volume. The original gauge was 500 milliliters, but in liters is 0.5 liters. Alright, now we have the proper units. Plug it in to solve for the molar mass of this gas. It is 1.81 grams, 0.08 liters times atmospheres over moles times Kelvin. Alright, temperature 400 Kelvin divided by 2 atm multiplied times 0.5 liters. So 2 times 0.5 is just 1. So it's going to be 1.81 times 0.08 times 400 gives us 57.9 grams per mole. And that is our answer for example number 8. This also brings us to the end of this lesson and also to the end of Unit 4. So thank you so much for watching.